So our next speaker is Brett Kennedy from JPL. He's going to talk about the trials effort of the RoboSimian team, and guess what you guys are doing now.
So before I go too far, I wanted to certainly acknowledge the other team members on Team RoboSimian. That would be Stanford University helped with we collaborated in the design of the hand that was used at the trials. Caltech and Joel Burdick's lab, ongoing collaboration with manipulation in particular, and Katie Bill's lab here at UCSB is handling both manipulation and mobility, with an emphasis on the mobility at the moment. So, RoboSimian. And I'm going to sort of speed through the beginning slides because a lot of you have been to the PI meetings, in which case you'll be very bored by these. So, but going back, we kind of see RoboSimian as being one end of the spectrum of solutions for these kinds of problems. So the least humanoid, the most generalized, and what can you do with that kind of system? And the hypothesized advantages there is by being slow and deliberate, you can make fewer mistakes, and that it'll actually mesh with the way that the systems might be operated by actual field teams. So the field teams want to be deliberative, the robot needs to accommodate that. Also, want to pick a system and a system architecture that's easy to build right now with today's technologies and implement in the field at the nearest point available in time. And then finally, trying to make this as generalized a system as possible. It's not really geared towards the finals or the challenge, but it can accommodate all of the issues that are presented by it, plus a great deal more is the goal. So the platform and its architecture can be applied across a wide range, but is not optimized to any particular thing. So now that I've said all of that, I want you to remember this slide later in the talk when I say, and then maybe not what we're going to do. Another considerable, an issue that we certainly wanted to tackle earlier than not is how the world actually accepts these kinds of robots. So anticipating the fact that there's the C-3PO problem, which is everybody wants their robot to be like C-3PO and nice and funny, or the Terminator problem, no one wants to be compared to the Terminator. We actually engaged with industrial designers and artists at JPL, and now we've extended that collaboration to the Art Center in Pasadena, and using their expertise in vehicle design and industrial design to come up with ideas about how this robot can be put together so that it meets its objective of being accepted as a practical solution. So this is not really an engineering thing, but the fact is if nobody uses our robots, it doesn't really matter how good they are at their job. Okay, so back to the engineering side. For the software, it's what you might expect from a practical solution. Pick the things that are hard for the human and let the robot do them. Pick the things that are hard for the robot and let the human do them. While we come from a tradition of letting the robot basically do most everything, right? Because the assumption is we're coming from your vehicle on Mars needs to take care of itself for the next 2 weeks. It may not do anything terribly sophisticated for those 2 weeks, but it needs to be able to take care of itself for that long and therefore carry that much autonomy. Now we're going to come back from that and we're going to walk it back and say, okay, well, given the fact that we could do it fully autonomously, let's walk it back and figure out what it is that we can do more efficiently if we insert the human. So the robot's doing the perception maps. It's got the good sensors. We don't really want to send the data back. It builds its own maps. It's got its own onboard behaviors that it knows how to execute itself. And then at the actual point of action, it's going to take care of its contact sensing and other things to correct for errors between what we think is the reality of the situation and the actual physics of it. The human then is going to do object recognition. So we don't really, while we might have some known objects, the assumption is that this robot probably is never going to know what a chair is. So the operator is always going to be in charge of telling it what a chair is. And then the operator is also going to put in primitive models into that world for the robot to understand So when it thinks about a valve, it doesn't have to think about how the valve works. The operator is able to put it in and say, the valve is this, and it rotates about this axis. Very quickly, for anybody who hasn't seen it, so the M&M Man, we started out with the proposal, then on to that artist conception, and then finally what we built. One of the things here is the fact that we ended up using these multi-modes, so we have a rolling mode and the walking mode. And then actually at the trials, a couple things to point out here. We talked earlier about how fast we can get this in the field as a practical matter. So one of the key things is that it fits in small boxes and can be shipped anywhere, and a lot of them if necessary. That the actual field station is as minimal as possible. We can run the entire robot off of one computer, monitor, and keyboard. That it's relatively portable, so there's no particular infrastructure to moving it around. And that we actually, to some degree or another, achieve that acceptance. This is sort of tangential to everything else, but I think it's an interesting thing to examine the generational aspects of this. I think we've found that the reticence of human beings to be around this particular robot is proportional to their age. So old people think it's creepy, young people think it's cool. So we might actually, this is wandering off in the weeds a bit, but the way we conceive of the uncanny valley, I think, might actually be a function of age. And so that there's actually a temporal shift to that valley depending on who you are and how old you are. So here's the debris task. I wanted to bring this up as an example of what it looks like. If I can get my thing to actually play. There we go. And one of the key things that I actually picked the debris for is this generalized thing. So we did a couple things in here. You can actually use it to just pick and place, as you might expect. But the other thing is giving the operator something that was general enough that they could play with it. And the key thing about the play is what do we do to actually get the most stuff out. We saw the bulldozer method, which we also tried out, and we're certainly considering doing because we thought it was a good idea. But the other version of it that we came up with was, well, what can we do just to pull that entire truss work out? And I don't know if you're all familiar with this or not. I personally would have loved to have spent a lot more time watching what everybody else is doing, but so I don't know if you guys have actually seen this or not. The idea is that we've got this nice rolling mode, we've got a way of grabbing onto things, and so we're just going to pull as much out at once as possible. Now we actually implemented this grabbing version of it for the finals. The other version that we had that was compatible with the practice truss work was actually a forklift version. So in the sitting mode, we actually had the flexibility of the ends of those limbs being used as a forklift. And so we actually went in, forked up the truss, and backed out with it. And that worked well as well. The eventual truss that we ended up with for the trials did not have the affordance for grabbing it in that forklift style. Okay, so very quickly, we didn't even try the vehicle stuff. That was as much a paperwork problem as anything else. The idea at JPL of asking the institution if it was okay if we used a robotic system to drive another gas-powered system was a bit more than we wanted to chew. Obstacle course, 2 points, felt pretty good about that, ran out of time. One of the key things, as you saw from the very beginning, was that this is a slow robot. It's not supposed to be a fast robot. Katie and her team are going to make this the fastest it can be. But frankly, it's just never going to be that fast. It's not conceived as a dynamic system in that way. So we got over a lot of it. One of the interesting things about it is our strategy for the trials was blind walking. So basically, it was running on force control throughout. So we talked at the beginning about the fact that we used force control and force sensing to correct for errors in our understanding of the world. For the trials, we actually, the entire obstacle course was a misunderstanding of our relative to the world. So it was simply just walking forward and stopping when it ran into something with its limbs. Door opening, ran out of time, but felt pretty good about it in general. We we jacked up the hands pretty good trying to open the doors. Popped a couple fingers. One of the other fun things in terms of the adaptability of the system to the problem was our solution to the wind was we actually opened the door up, and again, since we're in that rolling mode, we had that little distal end of the lower limbs. We actually popped that out, and just like you might if you're carrying something through a door, we stuck our foot out and kept the door open, and then we could kind of go through the door for the rest of the way. The ladder climb, didn't try it. That was both strategy and practice. It was on the first day. We didn't really want to, bang up our robot on the first day and endanger our chances for the second day. And the wall cutting. So we thought we had a shot at that. We tried it. We had exactly 1 day of practice back at the lab before we sent it out there. Unsurprisingly, it didn't go very well. It was our one intervention because we dropped the drill and we chose to go reset it and see if we could do it again. But not high expectations, and those expectations were met. So fire hose carry went reasonably well. Again, we did what we wanted to there, which was grab the hose and carry it. Threading it on was not something we particularly had time to try. And the valve closing, went pretty well. So a total of 14. So the lessons learned, and this is pretty high level stuff, right? One of the things I actually found most fascinating, not from a lesson learned from our own team, but in general being at the trials, was that all sorts of robots can be implemented successfully for these types of jobs. And I think as a community, that's an important lesson to have learned from this stuff. So out of the top 5, we had 4 different platforms, and all the way from the most humanoid to the least humanoid. So, 2, something we did and worked out really well for us is that we designed in this design and configuration flexibility, and we were ready to use it. So the wheeled mode, when I showed up at the PI meeting in Atlanta, which was about 6 weeks out, I think, if I remember correctly, from the finals. We didn't have this mode. It didn't exist. The parts didn't exist. So we still thought we were going to be walking through the entire finals. So in a span of about 4 weeks, we developed the hardware, developed the software, and tested it, and used it for all events except for the obstacle course. And that was because we were able to plug new actuators, which are actually the same actuators as in the limbs, and come up with, and our software was flexible enough to accommodate all of that. And that went really well. So, we saw the need, we saw where we were going to be otherwise, and so we chose the most effective solution for the trials. We tried very hard to get the right solution, which is this generalized capability of walking around and manipulating at the same time, but the wheeled mode was in fact just the most effective thing to do at the time. Build the operational flexibility into your system and let the operators explore it. So for a given physical configuration, is it generalized enough that there are options in how it gets used? And you saw that from the forklift mode, the sticking out of the foot going through the door, things of that nature. So we were able to build a system that when the operators used it, they could figure out different ways to use that system to accomplish different tasks. And actually, I thought that was one of the most exciting aspects of the system, because it really meant that it followed one of those early principles I was talking about, where it was a generalized thing that could be molded to the particular task. Translating human goals into robot goals is difficult. So humans make bad robots and vice versa. So trying to come up with the user interface and even sort of the mental methodology of translating what you'd like the robot to do into what the robot does is enormously difficult to do in an effective manner. You guys have all seen this, whether or not you work on DSC or not. So having your own mental flexibility is important, and then trying to come up with the tools that talk between the operator and the robot is enormously important. So the hand. So we came up with what we thought was a pretty cool hand, and it was pretty dexterous. It was certainly dexterous enough to do the job, but it was enormously difficult to build a hand that actually was robust enough to the tasks, not just the control, but also the tasks themselves. And it's an interesting lesson learned because even of the the most anthropomorphic hand that you could possibly come up with. Now, I don't know if anybody else has ever had an avulsion fracture. So we kept breaking the tendons in our hands. So I personally have experience with this. It's called jersey finger. It's got its own name. And that's what happens when you grab something hard enough and then forces exerted on the system and it breaks your own tendon. Right? So this is not unknown in humans. The big difference is that humans heal and robots don't. So we didn't feel very bad about the fact that our hand was not robust enough, because probably a human hand in the same situation would have had similar difficulties. Now obviously we have got a lot of other strategies as human beings to dealing with that problem. The fact that we have a much more sensor dense system helps a lot, and so to protect ourselves, but it's not a guarantee. So one of the things we're exploring right now is in fact what kind of hand do we need relative to the tasks. So it looks like making a more robust hand that has less dexterity is probably the right answer for the general set of tasks that we see in front of us. Seeing what you're doing makes things easier. You know, this is the duh, right? But this was definitely part of the experiment. One of the things about RoboSimian is that it had no hands, or sorry, it had no head, had no neck, and we were relying on our stereo camera coverage to get us where we needed to go. Now, for these difficult environments, we made sure that the system was compact. The problem being is the difference between being able to do a task like this and looking down on it and grabbing it, which is what we do as humans. That's relatively easy. Doing this is really hard, right? So this is basically how RoboSimian sees the world. And you get your limbs in front of your cameras a lot. The other issues we had is that we didn't implement all of our cameras, so we couldn't actually see our back limbs. So our walk maps would basically expire. And so this is something we're still looking at. So what do you do about that? What's the right balance between protection of your system in real world environments versus its ability to do its job? We definitely biased ourselves towards protecting ourselves in real world environments, but at the expense of our performance. And then the second is walking quickly is hard to do in a quasi-static manner, right? There's just a limit to how fast we can cycle through the limbs and plan for that. And that makes us slow. Again, duh, we knew that was going to be slow, but is that going to be fast enough to be, reasonable and competitive, which are not necessarily the same thing for sure. So what are we going to do about that? Okay, so make mobility faster. I'm going to leave that vague for a second. Achieve more of the design promises of the robot. So implementing strategies like whole body planning that actually allow us to meld the manipulation with the mobility so that we can stay in walk mode or in that quadrupedal or tripedal stance rather than switching over to wheels would be great. Some of the other, down in the hardware, revising our hand design. So this is something not quite ready for prime time, but I will show people not too distant future once I actually think it's going to work. And then solve the camera coverage and obscuration. Again, I'll leave that somewhat vague for the second. Software, whole body manipulation planning. That's what I said, trying to deal with the world in a combined manner where we're going to be able to manipulate and be mobile at the same time. So can we generalize the problem? How do we put those two things together? Mobility planning to avoid configurations where we can't take another step. This is sort of how far down the road can we look? And we can get ourselves in basically configurational cul-de-sacs. And as we found out, not only are they a cul-de-sac going forward, but sometimes it was actually difficult to figure out how to back it up. So that's one of the things that we had, particularly in the obstacle course, as an issue. Mobility planning for where to go body placement of manipulation. This is, I think, one of the things that we're most excited about is, again, looking down the road a little bit more. Let's pick the standoff, not only position, but pose that gives us the most capability for the manipulation task as it is. So that's planning one step forward, or one step ahead for where we're going to go. And taking that actually, again, this is something that the robot's going to be much better at, the planning software is going to be much better at, than the human operator. So what we had been doing is just saying, go to point B from point A, and then try to manipulate from that spot. And it was basically the operator's best guess what the best spot for point B to be was. And now we're going to try to let the planning software do that for us. Include the plan process on both robot and operator stations. So this is just a practical thing about how much data is going back and forth. And so we can let because the planner, as we had implemented for the trials, was just on the robot, every time we wanted to try something, we had to ask the robot basically, what do you think is a good plan for this? And the robot would send back what it thought was a good plan. In this case, what would like to do is let the robot keep that level of autonomy as necessary, but also include an identical version on the operator station so the operators can run through a bunch of scenarios on their own as well, without having to exchange data with the robot. Integration of objects into the autonomy algorithms. So some of the other speakers had already talked about this a little bit, but we basically like to let the robot understand a little bit more about a simple world. So we don't have to tell it everything about a valve. It's may take some direction from the operator, but not necessarily all of it. And then update object maps on demand, right? So we don't want to, again, we're going to try to only have the operators ask for those things when they need them. And then test a lot. So those vagaries I was talking about earlier, how are we going to actually solve some of these going forward? One of the things that we're doing is somewhat radical, is just changing the robot. So one of the things we're evaluating now is whether or not this new robot, Surrogate, or Surge to its friends, is a better solution for this particular set of problems than the more generalized RoboSimian. Now, did anybody go to ICRA and see pictures of this before? Or is this new to most of the room? Okay, so it sounds like it's new to most of the room. So, Surrogate, I was talking about the configurational flexibility. Well, that little wheeled node thing we did, this is turning that dial to 11. So now, this is actually a RoboSimian limb, but we've implemented it as a spine. So now we have this highly dexterous spine, and it's going to go back up to a more traditional bimanual limb structure, and then, again, to a more standard head. So pan-tilt head at the top, and then it's all driven around by a talon base. So if you can roll, I think Tony might agree with me here, if you can roll or track, as the case may be, it's a really efficient way of getting around. It doesn't take a whole lot of thought on the operator or the robot's part to move around in that manner. So, anybody old enough to have seen Short Circuit? 1986. Yeah, all right, good. If you haven't, you should go watch it, because you will see something that looks a lot like this, which was very funny because, of course, we're sitting there and designing this thing from first principles, and it's like, hey, look, that looks like Johnny 5. So every now and again, movie makers actually come up with robots that make some sense. Now, some of the cool bits about this, other than the fact that we can now move around on flat ground really efficiently, is that the highly dexterous spine gives us a lot of advantages that we didn't have otherwise. For instance, given the overall weight distribution, we can actually reach almost all the way out. So we now have, between spine and limb, nearly 2 limbs worth of reach distance. Now, not all of that's dexterous, right? So the manipulability at the end of that is obviously very low, but we can kind of hold one base and move around quite a bit. So let's try video. So what you're seeing here is we've applied this whole body planner to this for the valve closing. And the key thing to watch here is actually, and it's not dramatic, but you can actually see the spine as it starts to turn the valve. You'll see the spine start to move. So now we've got a very large manipulation space relative to these tasks. The other thing that, hopefully recycle itself in a second. There we go. I apologize for the video quality. I wanted to make this small enough to send out. The other thing you'll see is actually the other limb will move itself as well. And what it's actually doing is keep maintaining the center of gravity within the stability polygon of the tracks. So one of the reasons that we can actually reach so far is because we can actually start to do something like this. One of the strange advantages of this particular robot is that the limbs are so heavy that you can move a significant amount of mass around just by kind of reaching out into space. This. So now that whole body planning, one of the things that we're trying to do is we evaluate, and we are doing that, evaluate RoboSimian versus surrogate, is maintaining the techniques so that they can go back and forth. So that same whole body planning applied to a RoboSimian problem. So one of the things that we really did not do during the trials, or ahead of the trials, was exercise the entire body to make things happen. We really just sort of walked up, and this is both for wheeled mode and actually that we were approaching it from the limbed mode, is walking up, planting our tripod, and then using one limb to do the manipulation. So they're decoupling those functions. Here, we're combining those functions. And you can see that the reach space of RoboSimian is considerable. And then finally, doing a much better job, and since this is all relatively intimate, if you guys have questions, I'm going to start pointing at Brian in the corner and Katie to explain exactly those things. If you've got detailed questions, is what we're doing. But coming up with better gait planning and footfall planning so that we can get across these obstacles in a generalized manner in the limbed mode much, much faster than we did before. Because that is, in fact, in my opinion, the right answer for the most complex of terrains, which is really what we're looking to try to do with this. This, by the way, is a lovely picture. So if anybody wants to visit UCSB, it's a very nice spot. RoboSimian's got a nicer temporary home up there than it does back at JPL for sure. So I highly recommend it. And then finally, and I apologize, this is not the same set that I sent out. I've added this video to it. This is actually streamlining the user interface as well. So this, we talked about incorporating the object recognition into what the robot can do autonomously. And so you're seeing our best and brightest of the user interface now. So rather than dealing too much with direction, now we're just sort of, the robot knows kind of what it's looking for, in this case a button. The operator can draw a window of attention, and then the robot's going to look within that window to find the object it's looking for, and it'll plan the behavior based on that. And then carry out, in this case, the button push. So we'd like to be able to get down by the finals so that we can get most of what we need to do down to that tablet form. Now, for the finals, would we actually try to run the robot off the tablet? Yeah, probably not. I think we'd want more flexibility. About the time we run across the surprise task, and you've got no way of accommodating that, I think we'll still stick with the user interface we had before with the computer. Yeah, so I can leave that up. You guys have, this is where to go for all the detailed information, other than asking these guys. Any questions? Great. Yeah.
So take you back in the weeds on your comment about the uncanny valley in age.
Yeah.
Is that a generational issue, or is it more of, as you age, you see more dystopian science fiction, and so you become a little bit more? I
don't know. I mean, I'd love to see somebody actually do some research as far as that goes. I suspect both. I think that there's also within the tradition a trope of little kids liking monsters, right? So I think kids are a lot more open as to what they think is okay and natural, although they have a pretty canny sense of these things as well. And I think it's also people, the younger generation, just as they're more used to seeing people walking around with smartphones and all these other things, so it's just part of the natural environment, seeing things moving on their own is, driverless cars and things of that nature, that's going to be less weird to see objects that are animated in a way that they haven't been previous to now. So it's a really good question. I don't know. But I think that we might be overly concerned about how the next generation is going to see these types of robots. I think we need to spend a lot of time dealing with the human psychology of accepting animate systems but it might be a much more flexible question than I thought.
How much redesign of your user interface and autonomy system is required when you, say, went from hand-based or before the four-limbed-based manipulation to the wheels, or even to the new surrogate platform? How flexible has that been?
Basically, no changes. I mean, all we're really doing is updating the actual model that the planner is using and the kinematics of it. But because the limbs are the same, they are identical. By the way, when we talk about surrogate, there is no difference in those limbs at all. In fact, they were RoboSimian spares that we just used a different piece of aluminum to bolt together. And all of the algorithms are identical. There's nothing specialized about them between those three different modes.
Are you doing any of the support polygon computations in real time? So like if you grab a handle and push on it and there's a force out here, you might measure that force and try not to get too close to some boundary of the support polygon and avoid tipping over.
No, I think it's a short answer for that. So yes, we would like to. At this point, we are not. What we are doing is affordance control. So once that we're in that space, it will notice if it's pushing too hard beyond. But those are basically boundary numbers. They're not specifically recalculating to the stability base. But it is obviously the right thing to do. It's just not something we've done to this point.
So now that you have additional degrees of freedom, how do you handle the null space? Or what do you optimize on trying to reach something and you have 14 degrees of freedom to control?
So we're using quadratic programming to solve that problem. The null spaces are so, I mean, we don't end up with null spaces from a trajectory standpoint very often because it's such a high dimensional problem, and the limbs themselves are so dexterous. So it's very rare for us just to have it fail because it can't find a way to get to where we want it to go. I don't know that I really answered your question very well.
I guess you now have many different ways to get to a certain pose of the end effector.
Yeah.
How do you decide on which one or what's your cost?
It's just the heuristic. Katie's got
I mean, for the mobility, a lot of it is, it's great we've got 7 degrees of freedom to stick the limbs. We kind of exploit, the end effector doesn't have to be straight down. We've got some heuristics like pitching it out to reach further. And we actually, one approach we use is we build up tables that have, for us, we're really trying to move as fast as possible. So if you want to move in a neighboring location, we're really trying to look at the worst case joint and make sure it moves the minimum amount. So we build up tables by coming up the grid. We look locally if you're going to move the arm. We start off with like some heuristic to seed that, and then we try to optimize it so that we can do it efficiently. A lot of it is just coming up with a one-to-one mapping from XYZ for the end effector. So we try to turn it into little bug. For XYZ of the end effector, we come up with trajectories for all 7 of those joints. For the manipulation, I don't know, say more.
And based upon the task you're trying to accomplish, there are different heuristic rules that are applied to the solve. So, there's the general minimization problem within, once you define the heuristic for the task, there's the minimization problem within the kind of figuring out the joint end of the trajectory. But essentially, there are task-dependent rules for reducing the degrees of freedom within the task initially.
But yeah, initially it was like Jacobian-based, trying to find solutions that would end up getting the robot, like Brett was saying, walking a few steps and then saying, uh-oh, like that worked great. Now what do we do? So our solution's been, it's the stuff Brian's been working on in my group, just to, when it's something like mobility, try to come up with one solution for one type of thing. So one set of solutions going through a doorway, another one complex room.
Okay, I think
that's built into the behavior.
Sorry, I was just going to cull things and get everybody out here. Yeah, I guess we're running into the coffee break, so if anybody wants to stay and ask questions, but if you want to leave now, go ahead. We're starting again at 11.
So, I can see you back in 11.